Good afternoon, everyone. Thank you for joining this technical webinar. My name is Jean-Claude Borrell, and today I'm very pleased and honored to welcome our special guest, Professor Chris Zeris from the School of Civil Engineering of the National Technical University of Athens. It's a great honor for our company to have him as a guest lecturer for this webinar. The title of the webinar is a post-failure investigation using Diana of the collapse of Caisson CI14 and the implication to the design. So Professor Zeris is going to present some of his work, and we are definitely looking forward to hear his presentation. So Chris, if you want to mute yourself, the stage is all yours.
Thank you, Jean-Claude. Good afternoon, ladies and gentlemen. My name is Chris Zeris, and I'm a professor and head of the Reinforced Concrete Lab at the School of Civil Engineering and Technical University of Athens. The topic of my presentation is relates to the analysis we did a couple of years ago using Diana for a post-mortem investigation, a forensic investigation of a caisson failure in the port of Piraeus in Athens, which happened during the construction phase of the caisson there. Through this analysis, we also have some implications to the design of such structures. They're fairly common for the construction of port facilities, so we would like to share them with you. So, if just to give you a short background of the project on what happened. Basically, on the night of 27th of November 2020, during the final immersion phase of a caisson in the final position, where this is submerged, is synced into position on a pre-constructed rockfill bed in the final position of the breakwater, this caisson, just about 30 centimeters before touchdown, practically, there was a breach of a bulkhead cover, which was the top of the caisson, which let in one of the chambers inflow of seawater. So there was a differential head of water between the neighboring compartments of the caisson. And basically this eventually in a few hours, this could not be stopped and the caisson imploded, basically, and failed. There were no casualties, nobody was on the caisson, everybody was on the barge next to for the sinking operation. So this caisson was part of a set of 60 plus caissons of similar or slightly smaller dimensions, which were to be constructed on the full expansion of the passenger port of Piraeus, the phase A, in order for the port to be able to accept the large cruiser ships. So what was interesting about this caisson was that it was the second to be positioned in the permanent position. There was already a previous caisson, same size, same material, same design, same everything, which was constructed and positioned in place a month earlier, and nothing. There were no problems. There was no bulkhead failure either. But because this was a major project, and there were 4 more additional caissons ready to be sunk to the position, they were already constructed at the construction site, plus all the remaining were to be continued for the rest of the project. So the owners were and the independent engineer were concerned about this event, and they asked us to do a review, a complete failure investigation, a forensic investigation, to find out, review the design procedure of the designer, evaluate possible causes. Was it the fault of the bulkhead only? Was it the design flaw? Or what happened? Why did 14 fail and 26 did not a month earlier? And also to assess whether the existing caissons were suitable to be positioned using the same construction schedule, the same phasing of operations, or maybe there should be some recommendations to change the construction operations for the installation operations, or never the design of the future caissons. So all this was decided, and the results of this analysis are briefly given to you today. Let's see the typical caisson. One thing I should point out that this kind of construction was was not uncommon. The same contractor actually had constructed 2 additional port expansions in the COSCO terminal 5 or 6 years ago without any problems. Same procedure, but the only difference in that case were the caissons were practically about 22 meters tall. This was the first time where these caissons are 30 meters tall because the water is deeper in this location. In any case, so the typical caisson we're talking about is shown in plan and in cross-section in this slide. They are reinforced concrete constructions cast on a mud foundation. The foundation is 32 by 22 meters. The thickness of the foundation is 1.75 centimeters. The entire caisson is partitioned through interior diaphragmatic walls, which are shown in plan here, every 4.8 or every 6.5 meters in the 2 directions. The only particularity of this caisson, which was used in the previous construction site as well, construction jobs, was that because the caissons are constructed in dry and then in wet conditions using slip form operations, in order to facilitate the slip forming, the contractor needs a void in the interior of the moving floor, as this caisson is slip formed from elevation 0 at the mud foundation all the way to 29 meters height, so that in this location here, during slip forming, which lasts about 7 days, there is enough storage area for the reinforcement to be positioned, which has to be continuously erected during slip form, and also for the controls of the hydraulic equipment that manage the slip forming operations. So this chamber here results in a void basically throughout the depth of the caisson, which is remaining in the middle of this cross-section of this plan. The mixed design, the caisson is made of, according to the design specification, a C30 concrete, which is ready mixed on site. There was a batch plant operating on a 24-hour basis because the slip forming needs a continuous supply of concrete, and it's a non-stop operation. So once it starts, it finishes after about 9 days, 8 to 9 days on a 24-hour cycle. So the entire caisson is constructed non-stop practically. The concrete is slip-forming suitable concrete. So the requirements were with several admixtures which are being used. The concrete has to have a fairly fast, early strength so that it can support the slip form operation. And it has to be over the height of the slip form at the top of the form when it is cast fairly workable, so that the operation can, on a non-stop continuous casting operation, can accept the remaining concrete layers as they come in. So practically the mixed design was which was C30, as I said. It gave 3 days 45 cube strength megapascal compression strength, and then 7 days 53, and then 28 days 59 megapascals cube. These are lab standardized tests, so that was the preliminary mixed design, of course. And then we can see here the typical ballast. The way this slip forming is constructed, basically, the initial casting is done on a barge. You can see the barge here, which is long enough to support 3 caissons, 2 32 and one shorter one. So once the mud foundations are, the reinforcement cages are positioned in place, the mud foundation is cast. Then this barge is sitting next to the construction site, next to the land. So as soon as the first 3 meters of the walls are cast using ordinary casting operations, the slip forming starts. And already as the caisson goes up, it gains weight. So the barge sinks gradually, and at some point, the entire caisson and the mud start floating at sea level next to the port. The barge is removed and moved for the additional new caisson construction. And now these caissons are continued to be slip-formed near the port, and as they gain height, they continuously go deeper and deeper into the sea level. So this is the flotation condition, and at some point there is some ballast water added there in order to provide stability for the final height of the caisson. So the flotation phase of the caisson is practically finishing on the fifth day, and already the caisson at that time is about 15 meters tall, and 9 meters of this caisson are inside the water. From then on, the caisson starts raising more continuously using slip foam in order to reach the final height of 29 meters, and at the same time, the additional ballast water is provided inside the caisson, so that eventually the freeboard remaining outside the sea level next to the port, you can see here, is about 7 meters, and the rest is floating inside the sea. So practically this caisson at the age of 3 days is already in seawater, the mud foundation and the bottom of the shear walls, the way it is constructed, 4 days. So once this is completed, the caisson is taken by a tow barge, and it's taken to the final submergence position, the installation position over the bedrock, the rock fill, and there additional ballast is slowly put in the caisson. The caisson gradually sinks until it sits at the bottom, being full of water in and around the seawater. From then on, the construction backfilling of the caisson starts. The caisson is backfilled with boulders and excavation material from the port, or imported boulder material, aggregate stone material from quarries. And then once the caisson is completely backfilled, the final phase is to construct a 1 meter, 1.5 meter deep slab on the top, which connects the walls together, which is the floor of the port facilities. And then this completes the particular piece of the breakwater, practically in position. The full caisson line is positioned one after the other, using in controlled operations, and this is the way the entire port is constructed. So this was the second caisson to be positioned in phase. Let's see the design. Now, the design of the caisson there is no specific European norm for caissons. The only international code which is existing, I was told by the designer, for this kind of port facilities is the Japanese technical standard for port and harbor facilities, which was adopted in this situation. Practically what we're discussing and what we're investigating is the construction phase, not the full phase. We're not interested in the remaining design loads, the seismic or the gravity. The only thing in jeopardy, if you like, or under investigation in this particular post-mortem study was the construction sequence, namely the way the standard designs these caissons is during two conditions, the afloat condition and the fully submerged condition, and in between, of course, which are the two load cases which I will be discussing, the flotation and the installation condition. Of course, the standard, because this is a transient situation, it's a construction phase only situation, requires for an accidental differential head between the chambers of 1 meter with that safety factors of 10% of 1.1 during the design phase. And the remaining loads are the service loads, backfill, earthquakes, superstorms, etc., which were not of concern in this study. So we will practically will be talking about these specific design situations. Okay, prior to do any investigation, we requested that the full design was given to us, and there was a review of the documentation, which was not just the design calculations, but also the conditions, the weather conditions during construction of the early September submergence of the Caisson 26, and the mid-November conditions of this one, concrete sampling and testing during construction, during casting operations. According to the codes, regular samples were taken by independent testing laboratory and were tested at 7 and 28 days. So all these were given to us. The final design, the regulations, and so all the data of the construction phase, the timelines, and also the test results of the material, which were all the materials were all found to be in the range of 60-65 megapascals according to the mixed design. So there was no problem from the in situ casting of the concrete, even 70 megapascals cube. So of course we asked to do additional tests. We requested to from then on to do temperature measurements of the concrete during casting of the future caissons, and also to have additional laboratory tests of early strength gain of the concrete, and sampling and testing of the tensile strength of the rebars from failed portions of this caisson to make sure that the rebar was okay and ductile. Reinforcing was B500 weldable according of high ductility, because this is a standard reinforcement which is manufactured and sold in Greece because of seismic conditions. So, and it was okay. And we also took course of the failed caisson from the corners to establish the strength of the concrete, both of this one and the 4 remaining on the port, which showed that the concrete, at least after a week after the failure and of this one, were according to the design specifications. So in order now to find out what really happened and evaluate, we devised an analysis set using Diana. We did basically 2 different analyses. One was because the caisson was sunk into position into the sea during 3-4 ages, 3-4 days, and then it was continuously cast through slip form, but sunk. The bottom of the caisson was continuously inside the seawater. We did a young concrete thermal analysis, a maturity analysis using Diana using the material properties of the as-built conditions. And also we devised 2 models, mechanical models now, a full 3-dimensional model of the caisson. There were some, because of these holes here, these are the typical holes that were created by the designer in order to absorb energy when it's the leeward, it's the face facing the ship. So when the ship docks in the caisson, the waves which are generated are absorbed by these holes into the compartments and basically absorb the energy, the wave energy. So there was a slight asymmetry of the problem, and we decided to solve it 3-dimensional. And also, the problem was solved first to verify the design, the adequacy of the design as a linear elastic analysis. And then we went to nonlinear analysis with Diana always to assess the possible failure scenario and see which happened, basically what caused the failure, and isolate the causes. So I will talk about these 3 sets of analysis. First of all is the thermal, and then the 3-dimensional and a detailed analysis of the failure of a portion of the caisson using a more detailed model, where the first 3D model showed that there was a problem which affected the response of the entire caisson. Okay, so first, the objective of the maturity analysis first of all, the owner and the independent engineer, because this project was to be constructed on an annual cycle, on a 12-month cycle, construction cycle, they wanted to know not just the causes of the maturity gains, if you like, of the concrete or the caisson in the problem, but throughout the year, what would be the consequences of the seasonal temperature variations, which might affect future caissons. So the objectives were to assess the influence of the construction cycles on the maturity and to give some guidelines on possible delays in the construction sequence in order to let the concrete mature given the situations. So what we did is we did two quarter models for thermal mechanical models, as we show here of the caisson. Portion of the caisson was inside the seawater, exposed to the temperature of the seawater, and then the outside portion was exposed to the variational daily temperatures of the season, depending whether this was a summer or a November, fall, winter kind of condition, like the figure case. So we had two different ambient conditions for the air temperatures, and now the sea temperature was 19 for the season, for the summer, spring-summer construction schedule, 19 degrees centigrade, and 14 degrees centigrade for the case of the failed caisson and what would happen during the winter construction of future caissons. In fact, we actually looked for data. We found a diploma thesis at the university, which gave us the seasonal variation of the sea temperature in the Saronic Gulf, which changes between 14 to 25 degrees centigrade over an 8-9 year period. So this is how we devised the 14 centigrade for the minimum and the 19 to 20 as an average of the warmer case in the rest of the year. As far as the air conditions, these were taken by the weather conditions, which is available. And we had, again, two scenarios. One would be the fall-winter scenario, where the air temperature fluctuates over the day between 10 and 20 degrees. The air temperature in the spring fluctuates between 19 and 25 degrees. Of course, in the summer it gets warmer, but these were two suitable scenarios for the maturity. Of course, the concrete delivery temperature, we have shown that it's about 25 centigrade during the spring and 20 centigrade. This was measured during the delivery of the concrete in mid-November, where this was this failure happened. So these are the two models we investigated under boundary conditions. The hydration data for the model, we took directly the hydration data that Diana gives for the particular concrete grade, the C35, which was the in situ measured quality of the concrete, for the adiabatic heat development using the Japan Concrete Institute. But we actually requested measurements from the contractor, and we saw that the in situ measurement near the massive footing, fairly deep, which is a fairly adiabatic condition, gave a temperature gain over a day and a half of the order of 62 degrees centigrade, which was fairly close to the it was very close actually to the same heat development curve that the Japan Concrete Institute gives for this specific concrete. So we kept it. And we did the analysis. First of all, we wanted to verify that we can match the physics which we measured. So we did a typical sub-assembly of the caisson in the footing area, and we measured the temperature generated in the center and in the perimeters given this heat generation model, and we found that in reality the temperature near the weather exposed conditions was matching fairly closely, 62 degrees, the measurement over a day and a half. So we were fairly close to the temperature gain of the in situ measurement using Diana and the standardized material properties for the same concrete grade. So we went ahead and we did the maturity analysis. Now, in the two different scenarios, the fall and the summer conditions, we can see temperatures generated in different locations of the entire caisson quadrant. And we can see that this node here, which is below sea level, practically starts at the delivery temperature and sinks and stabilizes to the sea level fairly fast. So within 2 days, basically this area of the caisson stabilizes to a concrete temperature, which is maintained by the sea level, of course. So the same in the summer, but in this case, the the temperature of the sea is much closer to the laboratory condition of 20 degrees, which gives us the lab strengths. So if we do the peak temperature studies, we got out of this solution. In the fall, we had that the caisson was generated in this area here, 51 degrees centigrade at 15 hours, and then 56 in the summer. However, in terms of maturity, we looked at the maturity gain out of this analysis. Diana can give us maturities during actual time conditions. So we looked at the maturity of the concrete at 14 days after casting, because at 14 days, more or less, was the age where the submergence phase came for the caisson, the installation phase for the one that failed. And we figured out from the analysis that for the failure, the scenario which took place during the November, in fact, the concrete below sea level was actually at 14 days, was 11 days mature. So it was like 3 days ahead of the standardized strength that we would expect for this grade of concrete using like the Eurocode models. So one would expect a lower concrete strength at 14 days than one would calculate using Eurocode if you did an early strength gain analysis using Eurocode. In the summer, of course, we were, because the temperature of the sea was much higher, we were in line with the physical time, so the maturity was no problem. So the maturity was about 3-4 days behind. It was not that big a difference because the concrete gain is already fairly good at, like we saw from the lab tests. But in any case, just to be sure, we recommended that as a result of this analysis, that for the remaining of the project, we gave like a 10-day delay in the phasing of the submergence phase during the winter months, like November, December, January, February, where the temperatures of the sea are maintained at this about 14 degrees centigrade. So at least 10 days more delay. The caissons could still be constructed, but before they were, but only to float next to the port, before they were submerged to the final position where the stresses are fairly high and the forces, the hydrostatic forces, are generated and they need higher strengths. In the summer, this was not the case. The summer, we let the regular schedule to happen as approved by the contractor. We also recommended that they should do also in situ temperatures, ambient sea, air, and concrete during delivery for the entire length of the project. And also, what is the safest, of course, is to use cubes, specimens, which we call site exposed, not standardized cubes, which you send to the lab in order to break at 7, 14, or 28 days. But you leave them on the site. You can submerge them next to the sea, inside the sea, or you can leave them to be cured in the same conditions as the caisson above sea level, and you break them at 7 days so that you have like the site strength, the site maturity of the concrete is a good index of how the concrete is behaving before starting the installation phase. So this pretty much concludes the maturity analysis that we did. And let's move to the mechanical analysis. Now, the mechanical analysis, the objectives were 3. First of all, to verify the design. So we needed to have an elastic model, a linear model, in order to check and independently check the designer's calculations, and and follow up the design. And then to assess the capacity of the caissons as constructed, the caisson which failed, and also the caissons which were sitting on the port with much more mature concretes, because they were waiting now, in order to assess their capacities and figure out whether they could also be lowered to position. To identify then through this analysis shortcomings in the design and construction process, if any. We didn't know. And then to give some guidelines on that. So we did 2 models. First of all, we did a 3-dimensional model using shell elements with a mud foundation. We just show the superstructure here. But we used the entire caisson using regular curved shells in Diana. And then because of the response of this area here, given that the chamber in the middle gave a higher flexibility in this portion of the caisson under the full perimeter compression of the hydrostatic forces. And we did also a detail of this particular wall, full height, using brick elements and more detailed analysis to figure out how this wall here specifically and its mirror behaved during the submergence to see what happened. So let's start. First of all, the design verification. Of course, the guidelines in Japan don't do much on that. The designer used Eurocode Part 2. So Eurocode uses load factors, partial factor design inequalities, where the characteristic values of the material divided by partial material safety factors, 1.5 for the concrete, 1.15 for the steel, and then the load factor for the transient situation, which is also in line with our Eurocode 0, was 1.1 according to the Japanese standard. So practically the design check on a linear elastic basis was done using a linear elastic analysis and a C30 concrete, which was a design specification. Now for assessment, Eurocode doesn't give us much. Eurocode 8 gives information for seismic assessment, but not for regular assessment of structures. So we went to the model code, 2010 FIB model code, which provides a full chapter, chapter 7.11.11, for the assessment through inelastic finite element analysis of a structure. And in this case, the FIB specifies that the inequality, in order to have uniform reliability levels between design and assessment of the structures, one should use the inequality using mean material properties for concrete, mean as measured, but suitably lowered for safety, as measured during the time of interest, and divide the entire resistance of the item at hand by gamma RD, a safety reduction factor. So practically multiplied by 20% the load factor here in order to do the design inequality. And now the mean concrete strength is given FIB 1.1 times the characteristic value of the concrete with the ratio of the two partial factors between steel and concrete. So practically it's 85% of the in situ characteristic value. So since our caisson gave cube strengths of 60 megapascals, therefore this corresponds to about 80% of the cylinder minus 8. The characteristic strength was 40. So if we go to the 85% of that, practically C35 would be the C40 material would be what should be used in this analysis. But we used C35 just for the maturity. We gave it a little bit lower strength because this specific caisson was lowered slightly prematurely. And according to our calculations, this was more appropriate for the evaluation of the failed caisson. But for the future caissons, the existing caissons, which were already waiting for 2 months because the project stopped, we could use much higher because the in situ concrete measured by cores now, not by cubes during construction. We cored and we took samples of these from these caissons, and we could use through the same process C50. This was the appropriate strength for the future caissons. Of course, I'm not talking about those, but they were checked. They're actually positioned. They were found to be okay. They are already positioned. Plus, the project went on, so nothing happened since then. In any case, so let's see our model. The model now, we do a design linear and a non-linear assessment. Use regular curved shells, as we can see in the meshing operations. The reinforcement, which is the actual reinforcement, is provided through embedded sheets, each side of the shell. The mount foundation was included, and we allowed for a rotation here for the foundation. And we checked the two construction cases. The load cases, which we checked, basically were the flotation, the pounding, the installation, if you like, according to the Japanese standards, as well as the accidental case, which happened, which I should note, which involved practically this chamber here or that to have a regular, to be installed practically. It was more or less 30 centimeters above touchdown. So it was already sunk into the sea level, more or less. And already during the filling operations, this chamber overflowed compared to the neighboring chambers by 3 meters. So we gave it the flotation, the installation, and then the installation plus 3 meter differential in this specific chamber. So we will see those in the results. Now, the second model, because it turns out that the flexibility of this area here gave some deformations of the entire caisson, as it turns out from the three-dimensional model, we actually did a sub-assembly of the entire caisson, assuming full fixity conditions at this point by the perimeter shear wall, assuming roller fixity conditions because there is symmetry here in this specific area. So the sub-assembly was actually like this, fixed at this point, roller in this point, and then all the way down to the mat foundation. So we actually took a sub-assembly of this caisson under the hydrostatic flotation, installation, and then the differential load case again. In this case, we used brick three-dimensional elements, and the reinforcement was modeled using discrete rebar, I guess, again, embedded, not sheet reinforcement. So let's see the results. Now, the load cases, the standard load cases for the design, to verify the design as well, are the flotation for this specific caisson was this condition here, whereby the external sea level is at 19.5 meters, plus or minus 1, and the interior ballast water is at 7.5. So this is a flotation condition whereby the caisson is floating and then it's gradually filled in to let go to the installation. Now, the installation phase, the most critical, because from then on the caisson sits on the bottom, is when it is fully immersed in water, 28.5 meters. The bulkheads are still tight, unlike the one that failed. These are opened after the caisson is let in position and fully filled. So the most critical condition is where the interior, before full backfilling with ballast, is up to the point of 18 meters. These were provided by the designer, the coastal engineer who designed the caisson. So practically, in hydrostatic terms, the hydrostatic load in the flotation is this one, and the installation phase is this one. And we just did one additional case where this specific chamber was raised up to 3 meters from the neighbors for the failure case. Now, for the flotation, the design check and assessment, we checked both of these and the 1 meter design code specification using elastic analysis. And then for assessment, we did all of these plus the differential that showed the picture during the collapse of the implosion of the caisson. Now, okay, the elastic analysis, the original design was done by another program by the designer. So we actually run the same problem twice, once using Diana and once using this guy here, in order for the same load conditions and everything, linear elastic. And we actually, these are the results of the elastic analysis for the flotation condition. This is a load case using Diana. Of course, in the elastic analysis, the steel is inactive, but we let it in, doesn't make any difference. Still, the concrete was C30. In fact, we use the total strain crack model, which is supplied by the model, but in a linear elastic, it's using the material properties as a linear elastic solution. So if we look at the deformations of the flotation case, using the full 3D model, we can see that there is, of course, the flexibility of the inner chamber here during the flotation causes 4.3 millimeter cave-in of the perimeters under the flotation sea conditions. The bending moments which are created, these are the local axis shell moments. Local axes run along the perimeter longitudinal direction and transverse directions. And then the local axes run in this direction in the transverse chambers here. So the bending moments are given in this, in the vertical and the causing vertical reinforcement and horizontal reinforcement are given from the solution of Diana. And then we can see the check, if you like, between the two different softwares, the design software and the Diana, and the results are similar. We don't have much difference. The two programs gave similar results. We can see there is, like the flotation case, this is the typical grid line 3 and 4, which is this one here, the two walls across with the chamber in between. So the F12, the shear forces, which are developed because of the bending action of these shear walls as they cave in inwards, supported by the longitudinal walls, are shown here using the two programs, comparable. And now we go to the flotation, the installation condition, whereby the full sea level is imposed and then the remaining is 8 meters below inside, the most critical case. Now the deformations at the top crest from 4 become 11.4 millimeters. It's much more critical in this case because there is a much higher differential head over a full height here, constant, and all around the caisson. Again, you can see how the chamber affects this particular portion of the caisson. The remaining is fairly unharmed by the presence of this diaphragmatic support. And of course, it's a 3D analysis. So whatever we look at here, we also look at this here. So these particular walls practically don't move at all because of the continuity of these diaphragms through the longitudinal direction. Only the transverse is critical. And now the shell moments per meter are given here in kilonewton meters and in the two directions. And again, if we compare, we can see the negative moments, which are in the diaphragms, the positive moments, the sagging moments in the center, similar using the two programs. So the design is checked. And again, we can see now that the shear forces here are they fairly define a fairly constant distribution at the base, but from then on they die out. Practically whatever happens is in the bottom part of this caisson. Of course, we also solve the plus or minus 1 meter differential, which gives us the head to look at the moments and the reinforcements of these guys longitudinally and transversely, and they check. Now, let's see how the calculation of the reinforcement, how do we calculate the design reinforcement using in this particular caisson? Eurocode gives us design calculations for reinforcement, but Eurocode does not apply to caissons. It applies to buildings, bridges, or other structures. We only have a water tank Eurocode, but it's mostly related to cracking and serviceability conditions. So we don't have much there. So one can go to the bridge code and look, and the bridge code in the Eurocode 2 part 2 gives us a shell procedure to basically there is a sandwich model whereby the bending moments, out of plane bending moments, give us forces top and bottom in the shells, plus the membrane forces which come through the analysis. And this particular appendix L provides the methodology to estimate the reinforcements top and bottom of this shell in the two directions and mesh reinforcement. In fact, what the Eurocode does is it does all the envelope calculations, but practically calculates reinforcement forces at top and bottom layers. Practically the bending part is taken by these layers of the sandwich. The remaining part is taken is given to shear. And then this particular, given the lever arm of this particular force vectors, which translate into reinforcement, there is these are calculated And practically the Eurocode gives the bending part plus the shear by half in the top and bottom to devise reinforcement forces which translate into areas. And these have, Diana adopts the same procedure actually in the design reinforcement calculation according to Eurocode, with some special modifications on how the lever arm is calculated, depending on whether the caisson is at zero axial membrane force or compression membrane or tension membrane force. In any case, this is fairly pretty much the Eurocode calculation. Of course, this was checked, and okay, the calculations were Diana properly translates into reinforcement the bending reinforcement, the bending moments which are established by the analysis. One, however, can look at this caisson in a different way. Since this particular caisson, we had a lot of deformation of these walls in cave-in on a mat foundation. We have to consider these walls as being 30 meters tall. They're about 80 meters wide, long, 30 meters thickness, and then they rest on a mat foundation under a full hydrostatic effective load, which comes in from the perimeter, a differential hydrostatic. Now, this guy bends on the foundation and behaves pretty much like a cantilever. And this was the case during the submersion phase and the flotation phase. And of course, the elastic deformations of this cantilever were found to be 11 millimeters out of the analysis. So it's a cantilever with restraints from the transverse walls, which come in, introducing forces, membrane forces in these walls as well. So one can, instead of doing a shell elastic, one can do a linear elastic calculation of the reinforcement forces at the element level and use the bridge model for the sandwich forces to evaluate the forces on the membrane in plane of this particular cantilever. Alternatively, one could look at it as a cantilever and go to Eurocode 2, whereby Eurocode 2 gives us full information of how to design this cantilever as a member, as practically an I section. It's with a 8-meter part and then 2 flanges. And in this case, we can calculate the shear bending and axial force using Diana through a composed element, in fact, figure out the forces. And then if these forces here, or even from the elastic analysis, exceed the cracking under bending and shear force of the particular element of the center part of this beam here, then we should use the truss analogy and reinforce this particular wall for the entire shear forces generated as a cantilever using horizontal reinforcement, assuming a truss analog. However, if this is done, one would expect that after cracking, there is a moment shift, because this goes in the ultimate limit state with the truss analogy. In fact, Eurocode says that once you do a truss analog, you should shed half of the shear force into the longitudinal reinforcement, which resists parts of this shear. In fact, this is equivalent to the well-known moment shift. So one should move the typical moment diagram out of the unbalanced hydrostatic forces by lever arm times the cotangent of the angle. We accept theta is 45 degrees here. So we shift the moments. And in fact, what really happens is that the critical rebar, the fixity of this cantilever, has to be, in fact, extended over a full effective depth here, zeta, where the lever arm is practically the full width of this panel here, and then plus a development length. So one should anchor these fixed reinforcements here in order to accept the 45-degree crack, which is going to happen once this guy cracks under the lateral forces during the installation phase, which cracks moves the tensile forces at this level here. So, of course, we can do more because we can either reinforce this as a beam with horizontal stirrups. In fact, if you go to Eurocode 8, which is, I don't know, Eurocode is seismic, of course we use it, but they even give you some additional measures of how to develop the ultimate limit state beam reinforcement of this wall, and then use a good percentage of this horizontal reinforcement vertically in this area here, because these two directions interact under the 45-degree crack, and both directions pretty much have to accept this factored shear force. Significant in this case is the shear span, the effective shear span, which is the design moment over the design shear times the length of the wall, the zeta. So if this is less than 2, which and how this particular value, in fact, it was less than 2 for this particular restrained cantilever because of the restraints of the other walls. In fact, the cantilever has this kind of bending diagram. So in any case, the M over QL is close to 2. So one should expect to have the transverse and the vertical reinforcement in the shear area, in the shear panel, to be similar, to be equal. In fact, the only difference between these two is the axial force, but there is no axial force in this element apart from self-weight. Eurocode 8 handles buildings, not caissons. So in any case, we do have a region of a fuzzy region here of how to reinforce this thing. I would be more inclined. It turns out that the analysis showed that this model here as a beam was pretty much what happened during the composition, the deformation of this caisson, of course, but it did create the need to increase the reinforcement here in this region here. In any case, because the shell analysis does not really give us much at 45 degrees height between the out of the linear elastic solution. So let's look at the results. These are the typical membrane elastic analysis results. In the x direction, there's very, very little, actually, because it's a very high wall, but in the vertical forces are fairly high in these corners here. And then there is a constant shear practically over about a half length, which gives us a sandwich model, in this case here, of some horizontal and vertical reinforcement. But this was not the case in elastic analysis. Okay, so let's look at the inelastic analysis now. So we do define all the load cases times 20% up for the assessment. We use Diana, the total straight crack model, and for Mises plasticity for the rebar, the embedded rebar, and an unreal solution using Newton tangent stiffness with arc length search. And okay, these are the results. First of all, the deformations in millimeters of the nonlinear analysis, flotation, installation, and also the accidental installation plus 3 meters in the center. Okay, now in this case, the elastic was 4 millimeters. The inelastic goes 5.7. However, the elastic of the installation was, if you recall, about 11, 12 millimeters. The inelastic at load factor 1 is actually 30.6. So cracking is quite severe in the panels in this area here already. We are way off the cracking region during this service installation process. Now, if we allow this to overfill by 3 meters differential, the deformation pattern changes. We still have a 30.3 now millimeter drift in this direction, and actually less, it's 20, it's in the green area, so it's actually 23. But now we have a bulging out of plane of 33 because of the differential of 3 meters in the top. So the fact that this chamber here overflowed while the caisson was already inside the water changes completely the deformation shape and the critical forces here, as we will see. How is the crack pattern? Now, the principal crack width in millimeters out of this analysis In the flotation case, we don't exceed 1 millimeter in the base of these two walls, the interior partitions, out of the cantilever. Of course, in the installation, these cracks go up to about 1 millimeter. And then if we do the accidental, the cracks are actually different. They're not this much. They are no longer in the beam base, in the fixity base, but they are actually more important. That's why they cover, if you like, the colors in the contour plot, but they are actually in the sides of these walls. So these walls here practically are under transverse bending because of the differential head, as well as in plane shear because of the out of plane hydrostatic forces, the unbalanced hydrostatic forces. This is the case, of course, as if nothing would have happened. There would be no breach of bulkhead, and the caisson was, this is pretty much more or less what happened in the previous caisson when this thing touched down and everything went back to normal. Now, did we have any problems with the stresses? Concrete stresses are in the area of 14 in the flotation. No, actually, this is the peak, but in the case here, about 8 or 9 megapascals in this area because of the diagonal shears. When you go to the installation phase without breaching, these stresses increase to about 12 megapascals. The design concrete is C30, so we're okay, we're less than half. The actual concrete would be 35 or 40 or 50, depending on the maturity. So we're still okay. And then actually, if you allow for the influx of water here, these stresses are lowered, actually, they drop. And because there is more tension introduced in this chamber. And now let's look at the steel stresses, the vertical reinforcement stresses. In the flotation case, where the yield reinforcement is 500, the average value is 550, if we use mean values for the steel grade. So in the flotation phase, we are elastic. In the faultless installation phase, we are still elastic, about 290. In the peak, actually the peaks are in some areas here. The actual force stresses here in the vertical direction are less, they're about 235. And then however, if we go to the installation plus the failure, the imbalance, we see that already at unity load factor, we are actually already in this area here, which is the edge of the out of plane bending, we exceed yielding. In this, the bulging of these walls through installation already at unity include yielding of the longitudinal steel, which was framed in this location here, in the YY. Okay, so we decided to look at this particular subassembly more carefully using a more detailed model. Again, we do an assessment in elastic only now. We did an elastic check just to check the model, but it's no real bother. Now, again, we do same kind of materials, same kind of material grades. This is the typical longitudinal and transverse reinforcement, stirrups included, as embedded rebar now inside the walls, including all these triangular thickness zones, which is part of the design. The full cantilever height. This is the fixity side. This is the fixity with the mirror rollers, because there is a mirror, same compartment at the edge. So these are the load cases, flotation, submergence, and then submergence with 3-meter differential between this and the neighbor. So again, we look at the three cases. Now the flotation. Now pretty much the case is the same as in the shell analysis. 4 millimeters in the maximum in-plane bulging of this chamber. But you can see that already this behaves as a cantilever, pretty much fairly down. So actually, the shear deformations are pretty high down here. this more or less behaves as a fairly constant cantilever. And then the crack widths in this case, we do have a 0.2 millimeters in this area. In the fixity, the principal crack is actually at the bottom of the continuity to the remaining caisson here. So already the longitudinal walls start cracking. So really, what really caused cracking was because of the deformation, the cantilever deformation of this internal partition. Already cracks develop at the lower third of the external wall, which is 45 plus the cross-section thickness here. So, and then the crack 3, we have cracking in the 3 directions here. If we look at the installation phase now, unity, so because there is a load factor of 1.2 at 86%, and now we do have already this model deforms at 50 millimeters, fixed here in the chamber, and the crack widths are already now up to 17 millimeters. But look at the crack widths. We can see that the crack widths are developing over not just the full height of the exposed wall, which already started cracking during the loading phase, but all the way up. This crack actually continues in the midspan of the chamber, and already we develop 45-degree cracks of the cantilever as a beam, actually. So the full cantilever truss analog, if you like, develops in this particular I section with an effective stiffness here, an effective compression side, and a tension side. So actually, the cracked model is much more close to the distribution of forces we should expect, the tensile demands of this specific area, as opposed to the linear elastic predictions of the sandwich model. Of course, we can see that here in the stresses. You can see that the stresses already here in this 45-degree, if we look at this rotated, we see that the unity of the installation, we define here already some yellow, like 250 megapascals of the steel in this area here. And in the, actually, if we want to see that where the maximum, which is somewhere hidden in here, developed, we actually go back a few steps. So at the step not 86 intensity, but 80% intensity is the first actually, is already the stresses here are already elastic. The reason I'm going to 80 is because of the next load case, which I'm going to duplicate, to impose on this specific submergence, the 3-meter differential. Okay, so let's go to the differential case, which pretty much shows a picture of the failure. Now, in this case, which is installation again times 1, again 88 times 1.2, plus the differential. Now we can see that there is the full deformation is now 12 millimeters, and it's actually here because of the 3-meter differential between this area here and the remaining. So there is a big out of plane bending of this transverse wall, which should not have been happening if the breaches were not happening. Now we see that the actual crack pattern, again, concurrent with the installation phase, changes completely, and we have a full zipper crack all the way in the middle of this. So we crack not only in the supports, but also in the middle out of plane here. And now we see the stresses. The stresses are actually developing yield at this load case here, higher than yield actually, and a little bit higher in the entire height. So if we move back this load case and we go to 80% installation plus out of plane, this is the onset of yielding in this area here. So this shows what really happened. I mean, at 80% of the differential plus installation, yielding starts in this area here, and of course this goes This is the first onset of yield of this specific caisson. If we look at the same load factor here, 80%, where this is only installation stresses and forces, yielding here would not have happened. We would be already 350 megapascals in this area, actually much less, because there is no differential. Therefore, the stresses here were pretty much elastic. So this would be the case of the installation phase without any breaching of the chamber, which happened more or less in the caisson which was submerged a month ahead, assuming the maturity was the same, because maturity was better in that caisson because the water was warmer. So pretty much this concludes the forensic part of the study. We see that the actual case verification shows that, in fact, the procedure is problematic. We are fairly close to a reliability of like a load factor of 1, if you like, 1.1 in the, assuming no unforeseen events happen, like this breach. Of course, the breach failed the caisson, but we want to make sure we don't want this to happen in other caissons. So really, the results of this analysis and the recommendations were that the failure of the caisson occurred because of a concurrent in-plane deformation of the cantilevers, which started cracking the caisson, brought cracking into the caissons, but not yielding. And then once we were fairly low in the touchdown level, the breaching of the 3-meter observed differential chamber practically killed it. It bulged the centroid chamber, and the internal walls yielded, failed, and the entire perimeter caved in, according to the picture by drone that was taken the day after. So the caisson could have taken the installation loads, in fact, like the previous caisson, but the conditions were fairly tight. I mean, the load factor was about 15 to 10%, 15% lower than Unity. So assuming maturity problems or some other unforeseen cases, both the designer and independent engineer, we all agreed that we should boost up a little bit the procedure. So the recommendation was, first of all, to implement the maturity protocols to make sure the material was fine, and also so allow for delays for maturity gains. And then given this redistribution of stresses, and because really the elastic solution is not a good picture of what happens there after cracking, one thing that was proposed by the designer was a different protocol for the overfilling of the caisson in order to install it. In fact, in order to revert the inner caving of the chambers, the chamber was filled with higher water level first. There was a differential level of water imposed in the chamber to unbalance, if you like, an anti-force in order to take the external compression forces and remove somehow, as much as possible, the bulging inwards operation of the cantilever because of the presence of this chamber. So the cracking could be alleviated somehow more by the overfilling of the chamber differentially during the flotation and the sinking phase. So this was implemented in all the future caissons, and from then on, and there was no other problem. And also, just to make sure, the bottom reinforcement in the maximum bending region was actually continued over one full width of the panel width plus one development, horizontally and vertically, with additional stirrups in there, in order to make sure that the bottom part of the caisson in the lower 5-6 meters were well reinforced in case a 45 diagonal crack would like to form by any means, in order to keep the deformations and the stresses as they should be after the cracking. So this pretty much concludes my talk. I appreciate your time, and thank you very much. I will pass the microphone to you, Jean-Claude.
Thank you very much, Chris. I mean, it was a very nice and comprehensive presentation about a very interesting case. So it was nice to see, Diana apply to this case. So I'd like to thank you under the name of Diana here and also from the audience, because I also received some personal message from the audience, and they are very pleased with your presentation. So I'd like to pass that to you. It was very well received. Apparently there are not specific questions, or maybe it will come later by email. And in that case, I will share them with you. But what I read is mainly to say a great thank you to you, Chris, for this very nice presentation, which was a great case. So I pass this congratulations to you from the audience.
Thank you very much, Jean-Claude. Thank you all. Appreciate your interest in my talk. I have already given the PDF of the presentation for your.
Yeah, I sent a message to everyone. They can get the PDF.
And for Diana, any questions you may have or comments, I would be happy to answer. Okay, thank you very much.
Thank you very much, Chris, and thank you very much to the whole audience for coming to this webinar. And keep an eye on our website. There will be more events, especially after the summer break. And one more time, I'd like to thank you, Professor Chris Zeris, for taking the time to give this very nice presentation today. Thank you all. Have a good day.